All right. Well, hello everyone. My name is Matt,
And my name's Akosh.
and we're here from the Boston Consulting Group. We're in the Gamma division of the Boston Consulting Group, which is BCG's advanced analytics team. Bit of information about the Boston Consulting Group, because I can imagine that it might be a new name to some of you. We were founded in around the 60s by a guy named Bruce Henderson in Boston. That's also why we're called the Boston Consulting Group. At this point, we're a completely global firm. We're like active on all continents, and we really focus on management consulting. We focus on about like 20 practice areas, so that means that like we cover almost all industries as well. Yeah, so during most of what we did is management consulting, and what we really saw about like 4 or 5 years ago was that more and more of our cases actually involve advanced analytics, and to kind of like capture all that knowledge and expertise within BCG, like all the advanced analytics cases were put under what the Gamma umbrella. So like, yeah, BCG Gamma is the analytics and AI powerhouse of BCG.
What we saw was the traditional consulting tools of PowerPoint and Excel don't work anymore. And that's a common misconception that a lot of people have about analytics consulting, is that you're just going to be working in Excel. You're not going to actually get to do any real data science. And that's absolutely not the case from Matt and I's experience there. It's very much real data science, using the exact same open source Python technologies that everyone has been presenting here today. So as Matt said, fully global. We've met a lot of people here who are looking for roles and potentially new jobs in New York, but also potential jobs in Europe or India. So for anyone looking, it's global. We sponsor visas. It's not just New York based. And further, from what Matt said, we've done a lot of work. It's an interesting opportunity because you get to see a lot of things from various practice areas. So there's things that are very consumer facing, so personalized marketing, or how you combine the data science teams within two very large organizations that already exist. We do product facing work, so building a scheduling algorithm or building a pricing or promotion tool. We've done operations work, so that's predictive maintenance work, or optimizing how a flows through a factory. We've done network analysis, so using some of like Network X or some graph databases to understand how like emails flow through a company, or understand how you're going to design like sales areas for various businesses, or understanding where you're going to put new store locations if you're going to enter a new city. So it's a lot of like any area of data science is something that we'll probably touch, because so many companies have these huge amounts of data they're just collecting and don't necessarily know what to do with. So we get to come in and help with that. We are not just data scientists. We've got data engineers, software engineers, architects, DevOps people. So it's definitely a full stack business.
Yeah, so to kind of give an example of the work that we've been doing, it's actually a project I worked on. We kind of want to highlight one case. And this is a partnership that BCG launched with KLM about 2 years ago. KLM is part of the Air France KLM group. It's a European carrier based out in Amsterdam. And it's a pretty big airline. And as you guys might know, airlines are pretty operationally heavy in their day-to-day business. And it's something that it's also a very competitive market. So using data is something that airlines actually have been doing for quite a while, mainly when it comes to revenue management and things like that. But recently also to kind of improve the operations in their day-to-day or in their whole business working. So yeah, we have a quick video that kind of like explains what we did here.
We are KLM. We are aviation pioneers, Dutch at heart. We dare to reach out, initiate, and explore new horizons. We are the Boston Consulting Group. We are known and trusted for our strategic advice and for achieving impact. We put decades of experience to work, taking our approach to innovation to the next level. Together, We leverage the power of artificial intelligence and new technology. Jointly, we offer solutions that will change airline operations with a huge impact on customer satisfaction and operating costs. We bring together BCG consultants, BCG Gamma data scientists, and KLM operations experts to solve complex operational challenges together. On heavily disrupted days, tens of thousands of passengers are delayed or rebooked. In this complex network, even a small change can have a huge impact. Today, our artificial intelligence already helps us to load luggage smarter. In the case of a passenger no-show, this technology reduces the delay impact on other passengers and makes sure that every passenger travels with their own bag. But we do more. Based on advanced prediction models, our tools enable us to make sure one delay doesn't impact other flights, create efficient crew schedules, and minimize the impact of disruptions for crew, network, and our customers. Our tools support employees with the right information at the right time. We enable them to make the best decisions, big or small, whether it is a single no-show or hundreds of delays. Together, we have taken the first steps. The next steps are to bring this technology to other airlines. We bring AI to life. We make it usable in the real world, today. Turning airline operations into a competitive advantage. Launching a unique and globally leading partnership between KLM and the Boston Consulting Group.
Yeah, so a bit of a promotional video, of course. I mean, I imagine there are no airline executives in this room, but if there are, like, be sure to reach out. So yeah, I mean, really what the video does show is that is just kind of like all the different aspects that come with like running an airline. Together with KLM, and that's really also what the video highlights, it's really like a collaboration. It's not much like a client consultant partnership. It's really together with KLM. We've built out 5 tools basically, and these 5 tools also like interact with one another. The video kind of went over them, but I kind of wanted to dive a little bit deeper in exactly how they work. Hold up. Basically the 5 tools are Pathfinder through Harbinger, and Pathfinder is plane allocation. It's kind of if you book a ticket, it will tell you what plane you are in. I mean, you can also choose a seat, but which physical machine actually flies that route is typically not known yet, and that's calculated about like a month to like 2 weeks before, and all the way to kind of like to like more day of operations tools that assign which pilot and which crew fly your airplane. The funny thing with all these tools is that they all interact with one another. So they're big optimization heavy tools. Most of the base of most of them are integer programs. I don't know how familiar people here are with mathematical optimization. From Pathfinder, which basically assigns the actual machines to routes, to Sentry, which basically at the day of operations when an airport is shut down or a crazy thunderstorm somewhere, which means that planes are grounded or planes can actually not land or take off, it reshuffles all the planes again to like Harbinger, which at that point decides like, okay, well, a lot of pilots come in late, they might not make their connections because we think typically customers only make connections, but it's actually pilots make connections as well, suitcases make connections as well. It re-optimizes which pilot and which crew flies on which plane, and maybe that sounds a little bit like peculiar to you, but you have to understand that pilot like labor laws, it's not just actually union set laws, but it's actual labor laws set by like federal governments are incredibly strict. Pilots can only fly that many hours, and if you have a pilot that cannot fly a plane anymore and the plane is in Fargo, North Dakota, you're in a bit of a trouble, right? Because you're not going to very quickly drum up another pilot. So that means that the pilot has to sleep. You have to get a hotel. It's like an 8-hour delay immediately on your flight. So making sure and keeping these things into account and optimizing for that are really big cost savers for airlines. So a quick overview of exactly what Pathfinder does. Pathfinder is the tool that assigns machines or metal or iron or birds, like airlines have like the craziest terminologies for just a plane, to routes. To do that, the main goal of Pathfinder is typically to just robustify the schedule. So what we build is the underlying input in this model is a delay prediction, which is, I cannot go into too many details. It's always intellectual property, of course. But it's it's basically an artificial intelligence algorithm that predicts what the delay is, and it feeds that into a big optimization program, basically like a robust optimization program that knows how to deal with these certain distributions by kind of like changing the underlying solution space, while still keeping, some sort of computationally tractability. That's typically a big issue if you actually start optimizing over uncertainty, in order to assign these planes to the routes. And at the end of the day, what you get is that it just reshovels a lot of planes in order to create a more robust schedule. So it maximizes robustness. But actually, the funny thing is, once you have that whole integer program set up with these distributions underlying it, there are a lot of other use cases you can really use this framework for, right? Because this framework is nothing more than a pretty precise mathematical representation of the operations that the airline has 2 weeks before. So if there are other things that you want to do, for instance, like maximize utility, you can actually do that as well by very simply swapping in and out the cost function. This is something we have done with an Asian carrier. It's pretty cool. I was not able to show the demo here, but we have a tool that just reads in IATA data, which is publicly available plane data. If you're flying, or if you're a relative of you flying, you can track a plane. You can see what plane that is. That data is just readily available. And you put it in this mathematical representation. You change the cost function to maximize the utility. You say you have to be on the ground for at least an hour because connections need to be made and the plane needs to be restocked with food and all that. And what you do is you could just see that we saw that all the routes that this Asian carrier had, it could actually fly with 5 less planes. So these things are things that for an airline are actually incredibly valuable. Because these 5 planes means you can fly them to other routes, and that just really greatly increases the revenue of these big carriers. And in another way, you can by changing objective functions or cost functions. It's nothing more than a simulation tool, right? So you can see all right, what would happen, or by adding in other constraints in this, you're what would happen if we actually force planes to be on the ground for 2 hours, because maybe the reservations department says all right, let's have planes on the ground for 2 hours because we have a very big airport, like you might have in Atlanta or in Dallas, and it would be better. We see if we increase it to 2 hours, more customers actually make their connections, and you can just see what the impact that has on the day-to-day business of an airline. As much as typically, the typical use case we see for airlines is to actually maximize robustness. And what you still see, of course, is that when the actual day of operations come, is that, a thunderstorm hits. Typically, unfortunately, we cannot really predict thunderstorms that accurately 2 weeks in advance, as you guys might know. And thunderstorms in particular are, especially in the United States, a big problem for airlines because it means that the airport is closed. People are you're just not allowed to be on the ground as an actual worker. So no one can load the suitcases into the plane. People cannot stock the suitcases. People cannot drive around. Not to mention that there's also a bit of a safety aspect that you shouldn't necessarily be flying through massive thunderclouds. So at that, once the day of operations actually comes, what you sometimes see in airlines, or quite often see in airlines, is that you just have to recalculate and re-optimize your whole doing of business, and that's something. This tool is called Sentry. It's actually something I've worked on myself a lot. And the interesting thing here is that the structure of it is relatively similar to Pathfinder. We actually typically don't even include the robustness or the delay distributions. Why is that? It's because 50 minutes out, things are pretty deterministic. You know what connections passengers have, you know what connections crew has, you know what plane needs to be where for maintenance requirements. These things are pretty set in stone. The only actual big problem that you have with these things is that if a thunderstorm suddenly happens over Chicago O'Hare and everything needs to be recalculated, you don't want this algorithm to come up with an answer, like 2 weeks from now, because at that point, useless, right? So you actually don't even want that answer to be like 30 minutes from now. You really want it within the next 10 minutes. And these massive integer programs are solved by branch and bound algorithms or other mathematical algorithms that have very, very near exponential complexity. So the real trick here is kind of more like, how do you deal with the mathematical formulation, and how do you use certain decomposition algorithms to actually really decompose this this algorithm in a way that we still come to like an answer within under 5 minutes. And to give you a little bit of an example of how big this problem is, I mean, we deal with about, you have a lot of binary variables that basically tells you, does this plane fly this route, yes or no? These binary variables, if you have 100 planes and 100 routes, that means you already have 10,000 binary variables. But if that plane can also, and that route can take off every minute of the day, you can imagine that these variables just explode quite fast. So you're typically in the millions of variables, and each variable can be 1 or 0. So the big solution space here is 2 to the power of a couple million. I mean, 2 to the power of a couple million is just so big that is something that a human cannot even remotely understand. I think there are 2 to the power 40,000 atoms in the whole universe. So you can imagine how big 2 to the power of a couple million is. So yeah, that's it's always interesting to work on these problems, to speed them up and to make sure that you do come to a solution. And really what we see a lot here is that basically once you actually are able to decompose them, and you can find solving algorithms that might not necessarily rely on libraries out there, writing them up in packages like Numba or other really easily to parallelize and quick Python packages is something that we leverage a lot. So
makes sense. So the second half of this talk is mostly is going to speak about how we use what certain frameworks we use within BCG to ensure code success from day one. So as an industry, consulting often has short timelines, managers that aren't necessarily technical. You're interacting with client side people who maybe are even scared of SQL or have never seen a database in their life, and so all of the complexity that underlies a data science solution is hard to explain sometimes, and hard to put into timelines. So there's a number of things we use internally to ensure that code is successful from day one, and that we can take a solution from a proof of concept. So for example, Sentry on one certain class of plane. So maybe just all of Americans one specific fleet that leaves from LaGuardia as a proof of concept, and it works every time LaGuardia has a thunderstorm. But then American would say, hey, now let's expand this to all of our airplanes and all of our airports in the entire US, and the runtime has to still stay under 5 minutes. And so if it's something like that, then you have to start thinking about these things from day one of your project to make it so that 3 months in, once we've developed the proof of concept, or 6 months in, you're not going to say, all right, you're going to be paying us for the next 3 months while we completely rewrite our code base, and you're going to see nothing for the next 3 months. That's not something that you can do. So the first couple of bits that we've noticed is to spend time early when you're starting a data science project to really define your project structure and a tool set. Whenever code is well structured from the beginning, it's easier to onboard new team members. It's easier to explain what your code is doing to people who are a little bit skeptical of machine learning algorithms. Whenever you want to start focusing on scalability earlier rather than later. So when code is modular, it's easier to maintain. It's easier to swap out components from one thing to another. It's easier to switch out data sources. It's easier to switch algorithms. So as Matt was saying, going from one class of linear problem to another class of linear problem, it's easy to switch whenever that bit is kind of abstracted away and you have a little internal API to say, I'm going to submit something to it and I'm going to get a result from it. And the internal details of it, as long as it looks the same, I can measure the quality of it, but then switch one out to another. And then finally, making sure that quality stays high in a space where tight deadlines are unavoidable. So ensuring that you're going through a robust code review process, ensuring that code components are tested, will lead to a solution that doesn't break when new features are added or when features are swapped out from one to the other. So there's six key principles that we've noticed for the more senior people in the room. Hopefully none of these really come as a surprise, but it's important to write them down and put them into a framework that every single team has whenever they get started. They start with making sure that version control is used for everything. Infrastructure is reproducible. That's a big DevOps principle. Clean, robust, modular code. We're not writing functions that are like 200 lines long. We're not writing functions that just say run the code. Documentation that's up to date, so anyone who joins the project, or if you're explaining what your project does to a senior manager or a director in the company, can understand what's happening. Making sure things are tested from the start. And then a good team governance process to make sure that one person is in charge of the code, a person's in charge of understanding where the data lies, someone's making sure that there's proper security procedures that are being followed, and then maybe a product or project manager on top of that to guide the overall development of the code. Git is kind of a funny concept in the data science space itself. From people coming into data science from a software engineering background, using Git or using version control is something that, of course, why wouldn't you? For people entering data science from more of a business analyst background who are used to kind of Excel sheets or SharePoint or something like that, Git takes a bit to get used to. And oftentimes tutorials that are using Jupyter notebooks, like a learn to code Python in 100 days type courses that are using a lot of Jupyter notebooks to explain, don't necessarily show you how you version control notebooks, don't necessarily show you how to create a branching strategy when you're adding code, don't necessarily show you how you deal with code that's not necessarily code that you yourself wrote. And so starting with a Git repository, defining a branching workflow, so feature branches, hotfix branches, bug fix branches, run branches, for each various class of thing that's running in the code is important. Creating small branches is something that we've seen that works really well. Sometimes new developers can struggle with that whenever there's just here's all of my changes to the code in the last 2 weeks style branch. Those are really, really hard to review. Don't do that. And then pushing and committing regularly so you can always revert or roll back code that you wrote, and then something breaks or something doesn't work then as expected. Making sure that you can always revert back to a previous state, but that's a previous state that was maybe 2 or 3 hours ago, not a previous state that was 3 weeks ago. Second is code that runs easily on new machines scales much faster. This is a core principle of cloud development on AWS, Azure, or GCP. Things that install easily and require little configuration are great. It means you can spin up a new VM and automatically run your code on it if you realize you're running into size constraints, resourcing constraints. Things that only run on someone's laptop and are like very tightly bound to a specific environment are hard to scale. Then you have to invest a couple weeks in making sure that you're removing things like hard-coded paths or specific library versions, or even understanding what the environment that you're running your code on is something that can be hard to just like take out in the middle of a project. So starting with environment technology, or just environment best practices, using virtual environments, Conda environments, or Docker files is something that works really well and can let you port your code from one machine to another. Accessibility to the code is something that we like to focus on a lot as well. So not only should the data scientists be able to run the code, but ideally even business analysts or managers should be able to like do a run of the pipeline. So for example, with Pathfinder and Sentry, it's exposed as a website where they can put in input parameters, hit run, and then the code runs for them as well. So if there's a specific scenario that they want to test, they can do that themselves rather than saying, hey Matt, or hey Akosh, you're the data scientist who wrote this code. Can you run this scenario and that scenario for me? And I've spent my next 2 to 3 days playing around with configuration parameters and running the code instead of developing new features or making the code run faster and more robust. So exposing your model in a way that people can test it who aren't necessarily the developers themselves is something that works really well. And oftentimes they catch corner cases, edge cases that aren't things that the developers were thinking about when building the model. And then finally, proper abstractions in the code are critical. And nothing fancy on this one, just making sure that code is agnostic to like the directory structure. You're storing all of your files on an S3 bucket or an Azure Blob Storage type system, as opposed to just throwing everything on your C drive users or /home data type folder, and then whoever tries to run your code next is going to try to run it and get into a bunch of permissions issues and user directory issues and things like that. The next thing that we encourage all developers to use and all data scientists to use is assertions and logging wherever possible. Too many times, what ends up happening in code is we build these crazy expressive models. They're complex. They capture a lot of the complexity of the problem, and then it breaks. And then what happens now? And then you spend all of this time debugging the model and everything, and it turns out your input file for like this day, transactions for this day didn't come through, and it's a blank file. And you spent 8 hours debugging like what the heck is going on with my model that it can't handle this null, when it turns out that if you would have just ensured that there's more than one transaction per day, then you would have caught this as soon as your ETL process flags something. So data integrity on the input of your model, setting that up as soon as possible. And then also data integrity on the output of your model, because oftentimes one model feeds into the next model, which feeds into the next model, and then they're combined and transformed using various APIs internally. So ensuring that whatever comes out of a model makes logical sense. Then recording important events for monitoring and auditing. Each run of your code should ideally be reproducible. So logging like a Git hash to make sure that I can reproduce results whenever I want, or logging which versions of data I used on each run is something that makes people like trust the model more whenever they say, oh, actually, what happened 2 months ago and how is that solution different from today's solution? And then like doing an analysis like that is much easier when you've stored exactly what happened 2 months ago, and then you can recreate that result today. Documentation is kind of a tricky topic with data science solutions. They're complex. They're oftentimes hard to understand, and oftentimes there's a lot of stakeholders involved who aren't necessarily data scientists. So keeping documentation tightly coupled with the code through using what a lot of open source projects use, such as Read the Docs or MK Docs, is something that works well, even on internal projects, hosting them on an internal website. And that way your documentation goes through the same workflow as the rest of the code does. So it goes through pull requests. If there's an urgent update to the documentation that something has changed, that could be a hotfix branch, and then all users know. If there's like a website change or now they need to go to a different internal website, then you can immediately put that on the documentation. This also avoids a common problem with internal documentation structures at like large companies, where people just kind of spam documentation on various internal websites and it's completely unorganized and no one knows where anything is. If it's in the same structure as your code and it's PR'd and reviewed, then it makes it so that the documentation is something that at least a couple of people have seen, rather than people are just writing documentation and storing it wherever it makes sense to them. And then finally, writing documentation for both technical and non-technical audiences is something that we've found to be very critical. As someone who's writing a lot of code, it can be very easy to write documentation that's super technical. Documentation that's describing what your code is doing, and to your manager, or to really more your manager's manager, or your manager's manager, or some director somewhere, a couple levels up, like they don't care what algorithm I use. They care about like what's the general structure of this, how they can explain this algorithm that I built to an investor, how they can explain this algorithm to their boss. And so writing documentation on multiple levels is something that's very critical, both on the what is the code doing when someone tries to update it, but also what is the algorithm itself, or what is the general like story behind this algorithm without going into the underlying like implementation details necessarily. Then testing. Couple fun quotes, especially that one in top middle. It's very, very common as a data scientist to just throw out a model that works and just kind of runs and is hacked together. But two months down the line, 6 months down the line, your manager's not gonna oftentimes remember that you hacked this algorithm together in just like 2 days instead of taking a full 2 weeks to do it. But the poor quality and hackiness of it, when it still doesn't work 6 months later, you're trying to recreate your thoughts, that's going to stay until someone fixes that. So making sure that things are tested, things are easily extensible, and actually taking the time to do that is something that we've seen a lot of data scientists become better data scientists when they end up doing that. And then everything needs to be tested, even things that you don't think should be tested because they're going to break in the most unexpected ways. When it breaks, write a new test for it. When you encounter a new edge case, write a new test for it. That way, the code reliability is going to significantly increase over time, and you won't run into the awkward or embarrassing error of thinking you fixed something and then 2 to 3 months later, someone comes to you and says, "Hey, like I noticed this error. I thought y'all fixed this," and then you get to avoid that awkward conversation if you build a test case for it and make sure errors that are once errors are no longer errors. So to kind of conclude on this one, basically, what our internal philosophy is, any code that informs a decision process is considered production code. So whenever people use concepts like, oh, this is just test code, or oh, this is just like POC code, like it doesn't need to be like production grade. That's a red flag. Things that people are thinking, oh, this is just like, I'm going to replace this later. Those are the types of solutions that end up being heavily used by one of our clients, like 3, 4, 5 years down the line, and then no one's ever refactored it. So any code that anyone writes within Gamma follows these 6 principles. It's versioned, it's reproducible on any analysis. It's standardized using a standardized project structure, standardized Python tooling. It's well documented, it's tested, and it follows all of BCG's data and code governance best practices. So with that, we'd just like to conclude with a picture of Matt looking down in a marketing slide of we want to hire data scientists, we want to hire data engineers and software engineers. Come join us. We're growing fast.
We have a stand.
What's up?
We have a stand upstairs,
So come by, come get an umbrella, come get a pen. It might be raining, so an umbrella is actually useful swag. But basically, if you know Python or R and are interested in working on some of the world's largest analytics problems with some of the world's largest companies, we'd love to have you. Questions?
Can you talk a little bit about the engagement model, both between Gamma and your client service teams, and then collectively with your client?
Sure. So most of it, I would say most of it is kind of like, as I mentioned that earlier, is not necessarily like a consultant-client relationship, right? Where you come in wearing a suit, although I don't wear a suit, but like come in wearing a suit and talk to your, and be the consultant that says like this is the way things ought to happen or something like that. It's typically more like a very much a collaboration. What we often see is that the reason why it's a collaboration as well is because we are together also building out the client's capabilities to actually own the products that we build for them. So typically what we see is that sprints or other ways of working like are fully integrated with the clients, and that like a lot of teams that we have are not just only Gamma, it's also the client in there, it's also BCG Classic consultant in there. Sometimes it's also people from other verticals of BCG. like Platinian, it's more of an IT consultant like vertical that BCG has, and it's like all together as one group. We kind of like work towards.
So a fairly
yeah.
common framework that we end up using for a lot of engagements is that traditional strategy consulting BCG is working with an organization. They identify a use case that would work really well for an advanced analytics solution. They identify that whatever client would do much better with a significantly more robust pricing algorithm. And that's something that Gamma does a lot of. So then for a further phase of work, Gamma comes in, we'll build them something, and then we'll help hire data scientists that are going to take over this algorithm. So the first one we kind of might largely BCG, somewhat client data scientist. Then like the next use case that involves analytics would be like 50-50. And then like a third use case would end up being like mostly client data scientists and then like 1 or 2 BCG data scientists until they're fully equipped and capable to handle an internal data science organization. It's an interesting thing, data science consulting, because oftentimes the companies we work with, it's not Google, it's not going to be Uber, because data science is their core competency. Like they're not gonna hire a consulting firm to do that. A lot of the clients we work with are clients in the rest of the Fortune 500, so retailers, oil and gas, industrials, travel, hospitality. So clients where data is something that they can very much use, but they don't necessarily have experience hiring data scientists or building an internal analytics capability. And that's somewhere that we do a lot of work with to make sure that we use like examples of data science to help them as a business, but also develop them into a data-driven analytical organization.
It sometimes goes as far as like, here's our data, figure out what we can do with it, right? So they don't even know themselves like where this data can be helpful.
Anyone else? Do I just cold call on someone and make you ask a question? Yes, go ahead.
You mentioned that like many of the outputs from your models go into the next model.
Yep.
Does that like create like a chain dependency that can cause issues?
It can. It definitely can. So an example of a project that I worked on, an example of like the output of one model would work into the next one. So it was a markdown optimization model where you first had to forecast demand at various price points, which to forecast demand at various price points, you first need to calculate elasticities. And the demand at various price points would then flow into an optimization algorithm to generate the optimal price in a particular store for a particular day. And so it would be like a chain of models where first you had to calculate the elasticities. If you went to the Colonial talk yesterday, that's basically what they did, very similar model. Then that would go into a demand forecasting algorithm, and then that one would flow into an optimization algorithm, which is a large mixed integer program. And so that's why the slide that I was referring to a bit ago on ensuring that your data is valid both on the inputs and outputs of your models is very useful, because to debug the third model down the chain, you need to make sure the outputs of your first two make sense. And so it's easy to run into errors or like nonsense results by the like outputs of one of the further models that are down the line. But really, it turned out to be a bug in your first model, even though like that one ran through the pipeline correctly. So yes, do test. Test always, test often. As many things as you can validate, do so.
Nope.
Nope, no one else?
Well,
All
thank
right,
you so
well,
much for being here. Yeah.
Thanks for coming. We'll be upstairs.